Hello, everyone. Please join me in welcoming William Horton for CUDA on your Python, effective parallel programming on the GPU.
Hi, everyone. This is CUDA in your Python. My name is William. I'm really excited to be here at PyCon. This is my first PyCon ever, actually. How many people is this your first PyCon? Wow, that's a lot of hands. Yeah, everyone enjoying it so far? Sweet. So today, what I'm going to be talking about is basically various ways that we, as Python developers, can start to use the processing power of the GPU from our Python programs. And unfortunately, I have to start out with some bad news. Moore's law is dead. Sad face. Basically, Moore's law was the idea formulated by this guy, Gordon Moore, that the number of transistors in an integrated circuit would double every 2 years. And originally, he formulated it as an even shorter period, and he kind of adjusted the law. But this is something that has kind of been behind a lot of the advances in hardware. And he originally based it off of this data. So you can see this covers the period from the 50s, 60s, 70s. And on the left side, that's a log scale. So the linear nature of the graph means that it's growing at an exponential rate. And it actually continued to grow. This graph goes basically all the way up until 2016. And you can see that basically that same kind of trend of doubling every 2 years continued to hold. And then something happened. Physics happened. And basically, once you get, so this is actually a representation of the last time I took a physics class, which is why I threw it up there. So I'll give you a really high-level version of why Moore's law has started to fail. Basically, as we get down to smaller levels, I mean, the things now are on the nanometer scale. There's problems with fitting the transistors on the chips. There's problem with basically the power coming off of it and dissipation of the heat. So there's a lot of limitations that are starting to challenge this trend. A lot of people writing about it. People like to talk about the death of Moore's law. So the one authority I look to is this person who said, I guess I see Moore's law dying here in the next decade or so, but that's not surprising. And the reason why I trust this person so much is because this is Gordon Moore, and he said that in 2015. So I think we can be relatively certain that there's something going on here. And so the question is then, why GPUs? How can this new kind of device help us break through some of the challenges we're seeing in hardware manufacturing? So a little bit about the history of the GPU. They were originally manufactured for gaming purposes, for graphics rendering. And because of that, they were designed to be really good at vector and matrix operations, basically operating on sets of pixels or on objects in a certain scene. You can imagine that is requiring large matrices and then transformations on those. And so that was the original purpose of this device. So we can start to understand a little bit more about the differences between GPU and CPU by taking a look. These are two pretty recent high-end models of an Nvidia GPU versus an Intel CPU. And we can take a look at the specs. And we can see that the GPU, on the one hand, has many more cores, many more processing units. It has over 4,000 CUDA cores. The Intel CPU, 8 cores or up to 16 with hyperthreads. So you can see there's a huge disparity there in the number of processing units. While on the other hand, if you look at the base clock and boost clock rates, you can see in terms of clock speed that the Intel CPU is achieving roughly 3 times faster processing. So there you start to understand some of the differences between the GPU on the one hand, more processing but slower, versus the CPU, which has fewer processing units but can do things faster. And this is a diagram from the Nvidia documentation that basically gets to the heart of the difference between CPU versus GPU on an architecture level. And basically, you can see on the CPU side, there's large portions of the chip that are dedicated to control. So that's your if statements, your while statements, things like that. Whereas on the GPU, there's not so many pieces being devoted to that. You can also see the CPU has a much larger cache, whereas on the GPU, again, that's relatively small. And the green bits that are kind of dominating the GPU are arithmetic units. So basically, the GPU is packed with these smaller units that are built to do like simple arithmetic operations. And so on kind of a hardware level, this is the difference between CPU and GPU. And what people have started to realize is that the GPU isn't just useful for gaming. And so there's the rise of this paradigm that is called GPGPU, the idea that we can do general purpose workloads on a GPU. And this is from a paper published by Nvidia. But they're saying the GPU could be just a truly parallel processor. And different companies started coming up with different models to be able to do this kind of programming on their GPUs. So Nvidia did CUDA, which we're going to talk about today. But there are other standards. AMD has their own, and OpenCL is a developing open standard. But the main idea is people starting to realize that we've built these devices for a certain kind of workload, and that might be useful across many different domains. So why am I interested in this? Part of it has to do with my day job, which I'll tell you about. I work as a software engineer at Compass, which is a real estate technology company. We're putting tools in the hands of agents to make them more productive. And there I work on data pipelines and data ingestion. So we use some pretty common Python tools, including PySpark, Kafka, Airflow. And I will mention that we're hiring in NYC and Seattle. And I like to keep my ear to the ground in terms of things and new technologies that are happening kind of in this domain. And so one thing that's been proposed and is being worked on by Rapids is the idea of GPUs for data pipelines. So the idea that you might already be training your model on the GPU. And so why not do some other steps? Why not do data pre-processing? Why not do feature engineering? Maybe even do your visualization. So this is one thing that's kind of coming down the pipeline in terms of using the GPU for even more. This is another pretty recent article from this year where Uber actually used GPUs to come up with an analytics database. So these are just examples of ways in which the GPU is starting to be used in this space. But the talk also has something to do with my hobbies, which include deep learning. So I got into it through the Fast AI program. I've done probably way too many Kaggle competitions, mostly using PyTorch. And you can see here, this is a picture of my home rig that I lovingly assembled. I've got 2 Nvidia GPUs in there. Basically, I had to do that because one weekend I left my GPU instance running on AWS, forgot to turn it off. Monday, I woke up to a really, really big bill, and that's not good. So I decided build something at home. I actually came up with a little bit of a law. I've kind of repurposed the graph from before, but I'm calling this one Horton's law, which is basically the doubling every month of your AWS bill with your interest in deep learning. So this is just something to keep in mind. So another thing is last year I made a pull request to PyTorch, basically moving a function that had been in the purely Python side of the library into the C++ side. And so this also got me thinking about these kinds of problems. And if you ever look into the internals there, they're doing some really interesting things in terms of how they bring together the Python API with the C++ extensions, as well as accessing CUDA. And so this is another thing that inspired this talk and got me thinking about these kinds of problems. So now we get to the question that you probably all came here to answer. How can you start programming the GPU? So to illustrate how you might do it, I first wanted to give you a CPU example. So this is from NumPy. We're basically creating 2 vectors and adding them together. So 2 pretty large vectors. And so this is a NumPy example. I'm going to show you the example of how to do this exact same operation on the GPU. There it is. In case you missed it, OK, I'll do it one more time. Here's NumPy. OK, CPU, GPU. There's the differences highlighted. That's it. Thank you. So what we're doing here, also you can see I benchmarked this, and just that drop-in replacement, you can get up to a 30 times speed up using CUDA and using the GPU. So this is a really powerful approach. So to give you a little bit overview of what we're going through, what I just demonstrated was a drop-in replacement. So I'm going to talk about that a little bit. And that's kind of the simplest way, is there are libraries out there that will let you plug in to your existing code with very minimal changes and start to access this processing. The second one is a little bit more complex. It's basically compiling CUDA strings within your Python program. And then the last one is basically building your CUDA kernels as a C or C++ extension to your Python programs. And basically, as with a lot of things in software engineering, these are kind of in increasing complexity. But at the same time, as you go through these steps, they'll give you greater control over your programs and maybe access to certain features of CUDA that you couldn't have with just a drop-in. So to talk about the drop-in, the library that I just showed you is CuPy. It's basically designed as a drop-in for NumPy. It was developed for a deep learning framework called Chainer, and it supports a lot of the features that you might know and love about NumPy, including indexing, different data types, as well as broadcasting. And they've done a lot of work to make this work really smoothly, just like NumPy. But there are a couple API differences that I wanted to shout out, just in case you want to drop this into your programs. So one, there are certain data types that you can't use, which are strings and objects, just because the GPU would have a hard time processing those. The other thing is, if you do np.array, you can do that around a Python list, and that will work. But in this case, it won't work. And then the last thing is, basically, numpy.sum is going to return you a scalar, so just one number, and CuPy is going to return you, it's going to be an array. So you just have to watch out for those gotchas. But otherwise, it should be pretty smooth to plug this in and start getting speed-ups. And so I just wanted to mention a couple other drop-in libraries. And this is from Rapids, which I mentioned earlier before. There's cuDF, which is a drop-in for pandas data frames. There's cuML they're working on, which is aspiring to be a CUDA-powered scikit-learn. And I know they've already got some algorithms implemented. So definitely check that out if you're interested in bringing this into your workflow. So the next thing we're going to talk about is compiling CUDA strings in your Python program. And so when we get into this, we have to start talking about what is the CUDA API? What does a CUDA program actually look like? We're moving beyond drop-ins. And so this is the basic API of CUDA. A program is organized into threads, blocks, and grids. And so at the bottom there, you've got a bunch of threads in a block. The top is a bunch of blocks in a grid. And we're going to talk a little bit about basically how this is organized and also why it's important that things are organized in this way. So what is a thread in this paradigm? The thread is the thing that's actually executing your CUDA code. And it also has a thread index that goes basically up to 3 dimensions. And the thread index is important because it's used to specify which part of the data you're doing work on. And so the question might be, why can you index it in 3 dimensions? And this is a really useful thing in terms of understanding this programming paradigm and how you can use it most effectively. So GPUs are best at doing data parallel operations. So basically, if you have a bunch of data, let's say you have like 1 million elements in a vector, and you want to do the same thing. Let's say you want to double them. You want to double each of those numbers. You can just split those up, assign different ones to different processors, and then have them do it. And that's completely parallelizable and basically only limited then by the number of processors that you have. And so a lot of operations you do on vectors or matrices can be done in this way. So this is one example, is let's say you want to perform an operation on this. There's 9 elements. You have 4 threads. So you start to figure out, well, which one is the thread going to operate? And this is one way that you can assign it. To put it more clearly, basically the threads are working on different indices. And so thread 0 ends up being 0, 4, and 8. Let's say thread 1, 1, and 5, you can see. And the nice thing about this system is that you can code a rule for that, which is each thread, up until you get to the end of the vector, is going to work on one that is its own index plus the number of threads times I. And you would just go through I until you got to the end. And so this is a nice way of organizing these kinds of operations. But then the question becomes, what do you do if it's 2-dimensional? It becomes a lot trickier to start to assign indices to each thread, you could use modulo, and then you start getting all these kinds of weird calculations to just figure out what index you might use. 3D example would get even weirder if you have a single index for your threads, but then your data is in 3D. That starts getting very tricky. And so what CUDA lets you do is start looking at your threads in multiple dimensions as well. So if you have 2D data, why not also assign your threads in a two-dimensional way? So your threads also have two indexes, and that makes it a lot easier to map from a thread to an element. And basically, this is what this piece of the CUDA API is. So your threads are in a block, and you can index them. You can index them in 1D. In this case, it's 2D. You can index them in up to 3D to be able to map your processing to your data. And that makes your programs a lot simpler and a lot clearer. So then we've talked kind of about threads, how those are organized. So then we also have blocks and grids. Blocks are organizations of groups of threads. So this is one block. Basically, your blocks have to execute independently. So within a block, your threads are going to be executing together, but then your blocks have to execute independently. You should be able to do them in any order. And the other thing is, the threads within the blocks can share data between each other, but then across blocks, there is no shared memory. And so your blocks can also be indexed in up to 3 dimensions, and they also have a block dimension, which is also used in calculating these indexes. And then grids are basically just groups of blocks. So this is the whole, basically whole API again. So at the top, you have a grid, which is full of blocks, and then you take one block, which is full of threads that you can assign to these tasks. And it kind of matches up well with this architecture diagram we saw before, where each of your threads then are being assigned to the small green units on the right in the GPU architecture. So this is one example of a CUDA kernel, and we're going to dive into a couple particulars about this code. Basically, to understand it, we have to understand how does CUDA work across your CPU and your GPU. And you need both the CPU and the GPU because the CPU is going to be running some code in terms of getting the data, maybe performing some sort of logic. And then when you want to perform your operation, you're going to send it to the GPU. And so in the CUDA language, your CPU is called your host. The GPU, you could have multiple of them, are called your device or your devices. And basically, the CPU is transferring data to the GPU, and the GPU can send it back. So this is kind of the setup. And so what you have is a C or C++ style syntax, but with some additions to make you able to specify what code runs on the device versus what code runs on the host. And so that's the global is going to let you specify the actual kernel function, and then there's some additional syntax to be able to set up grid size and block size. And so this is it again. You can see it's using the global up top, and that means that function is going to run on the GPU. This main function is basically regular C++. That's going to run on your CPU. So let's talk about PyCUDA. What does it let you do? It was built by a researcher originally, and it's described in this, this paper. It's one of the few libraries I've encountered that actually have a research paper dedicated to it. So if you're interested in the internals, you can definitely dive into that. And it's been used in a lot of academic projects. So this is an example code of PyCUDA, and what it lets you do is it has this source module class that takes in a string that is CUDA code, and then from within your Python code lets you get that function and call it on your arrays. So this is the basic setup of PyCUDA. And what are the benefits of it compared to manual CUDA? One is automatic memory management. There's also benefits in data transfer, automatic error checking, and metaprogramming. So automatic memory management, basically the memory management in PyCUDA conforms to the Python way of managing memory. So once an object goes outside of its lifetime, it's going to be cleaned up. This is not how CUDA works. So if you were actually working directly with it, you'd have to do a lot of like manual allocation of memory, which we'll see later. Another thing that PyCUDA is nice about is data transfer. So this is some example code. It's using this class CUDA.InOut that PyCUDA provides. And basically, what you would originally have to do in data transfer between CPU and GPU is you have to create a NumPy array maybe on the CPU. You you need to allocate GPU memory, transfer the data between the devices, run the kernel, and then send it back. And so these classes basically will do that automatically for you. And so in, data is going in, out, data is coming out, in-out does both of them. And that just wraps the array in a nice way. Another thing is automatic error checking. This is from the CUDA documentation. If an asynchronous error occurs, it will be reported by some subsequent unrelated runtime function call. That sounds really confusing to me, personally. And so PyCUDA is going to wrap that, check the errors at the right time, and then surface them as Python exceptions. And finally, metaprogramming. This is a really interesting feature of PyCUDA and how you're basically using strings in Python to create your CUDA code. I talked about threads, blocks, and grids, and the size of those things can be hard to tune. So basically, for a given problem, a given workload, you want to decide how many of those to allocate. And that can be difficult, and it can impact the performance of your code. And so what you might want to do is benchmark different parameters of that. And because PyCUDA is compiling strings, what you can do is templating. So this is just normal string templating. And you're templating in different parameters for maybe the size of your block or the size of your grid. And so you can very easily write a Python program that loops over different parameters and then templates them into your CUDA kernel, and then use that kernel and time it and do some profiling there. So finally, we have CUDA as a C or C++ extension. And so when someone was reviewing this talk and I got to this part, they're like, why not just use C++? And I said, well, I'm speaking at PyCon, so. But the real answer is this is a really common paradigm across libraries. And this is what you would want to dig into if you are actually building something for Python users. So this is what PyTorch does, this is what TensorFlow does. But in a way, this is also what NumPy does, just with C or C++ extensions. They're letting you use a Python API, but behind the scenes, it's calling more powerful parts of your system. And so what I call this kind of version of using CUDA is Python API and CUDA performance. And so if this is a desirable thing for you, especially if you're building libraries, then you might want to go this route. So this is kind of the documentation about Python C extensions. You can basically build a module in C or C++ that you have then the ability to import into your Python code and call. And what this requires from CUDA is to be able to somehow translate it from CUDA to C or C++ to be able to make that connection to Python. And luckily, Nvidia provides a compiler called NVCC, which basically takes in your CUDA code, and it does a couple things. One, the kernel part that's going to run on your GPU device is turned into GPU assembly. And then it basically takes the rest of the code that's meant to run on the CPU. It replaces the special syntax that it's using. And then it can also just compile your CPU code for you. So everything can happen through NVCC, and that's pretty nice. In terms of the Python side, if you're interested, this is a really good place to start understanding, and this will be in my slides. Basically, what you can do, there's a couple ways you can do it. This way, which makes it a little bit easier, is you can use Python to generate a C++ class, and then by hacking a little bit in your setup tools, you can get NVCC to compile and link everything together. And this is just, if you've had to do extensions or worked in setup tools, this is just one snippet from that repo. Basically how they're setting up the sources, which is some CUDA code, some C++ code, and you can basically specify that you want the NVCC compiler to compile and link it together. But definitely check that out if this is something you're interested in, especially, like I said, if you're building libraries that are being exposed to users. And so some of the benefits of this is manual memory management. And you might say, well, is that really a benefit? But so this is what you might have to do. You can see there's like mallocs and mem copies. And you also have to do freeze, which is annoying. But there are some benefits to manual memory management. There's CUDA features. So like page-locked memory, mapped memory can be really powerful. These are basically ways to use the memory of both your host and your device together. And so you can get better performance out of these and save some of the writing that's going on back and forth. So this can be really powerful, and in order to access you need to kind of drop into the C and C++ extension. Another thing is a compiler. And I know I shouldn't say this because it's a Python conference. But I will say, as someone who is kind of putting this together and you're working with this CUDA code, it can be nice for it to just tell you you did something wrong, especially if you're unfamiliar with the API. And so I think this is a plus to doing it the extension way. And so finally, I just want to talk about how to get started. You know, you've seen this talk. You're interested in using the GPU. So the first thing is access. And the nice thing is there's a lot of resources out there that can let you access a GPU. There's Google Colab, which I think is awesome, and it's free. Kaggle kernels have free GPUs as well. And then even if you want to host it on your own instance, both AWS and Google Cloud have pretty cheap offerings. But I will say, if you go down this route, always remember Horton's law. Don't forget to turn it off. Finally, you know, where can you go next? One, I would definitely say, how can you apply CUDA to your own workflow? So like I said, it's starting to be applied in a lot of different domains, so you can think about how can it work for you. The other thing to get into is now that you have these tools to do parallel programming, you can start to do some research into actual parallel programming algorithms you can use with this paradigm. And finally, if you're interested in this kind of stuff from a hardware or device level, there's not just GPUs, there's TPUs, other XPUs, I guess is a term people use now. And also you can get into maybe FPGAs, which is kind of the extreme, going to the extreme of having the device that actually executes your algorithm. And so that, if you're interested in the hardware side, is definitely another place to go. And that is at the actual end. Thank you so much, and go program the GPU.